We'll wait 1 minute, 1 to 2 minutes to let everyone in, and then we'll start. Yes, I think most of the participants have joined the room. So first of all, I'll just welcome you all to this Brain Talks, Maritime Autonomous Systems and Aquaculture. Today we have 3 presenters. The first one is Stephanie Kemna. And after Stephanie, Rudolf will have a talk. And then at the end, Oddvar will have a talk as well. After each presentation, the presenters will answer questions, and you can ask questions at slido.com with the code 47546. We'll post this in the chat. So just go into slido.com with this code, and you can ask questions. So the presenters will answer these after their presentations. We have also made a quiz for the participants. So, and this is related to this talk. Answer this quiz and you will have a chance to win some great prizes. Yes, so then I will just welcome Stephanie Kemna to talk.
Yeah, thank you. All right, I'll just share my presentation. So thanks, Jill, for inviting me to give a talk here. So I'm Stephanie Kemna, and I work at Maritime Robotics here in Trondheim. I thought it might be interesting, so I'll talk to you a bit about AI and machine learning and other R&D that we're doing at Maritime Robotics. And I thought maybe give a little background about myself first. So I studied artificial intelligence actually at the University of Groningen in the Netherlands. There are several universities in the Netherlands where you can study AI. So I got the bachelor and a master's there, and I started working with the robots, amongst which the Pioneer robot and the Aibo robot dog, the old version. There's a new version now. And then after I graduated from there, I got a job as a researcher at the NATO Center for Maritime Research and Experimentation in Italy. So I worked there for 3 years on autonomy and mission planning for autonomous underwater vehicles, which are these torpedo-shaped underwater vehicles that you see on the images of on the right side. And I really enjoyed the work I was doing there and was interested in investigating some kind of deeper research questions when it came to doing adaptive missions and doing multi-robot missions. So then I went to do my PhD at the University of Southern California in Los Angeles, where again my focus was on marine robotics, and then specifically again working with autonomous underwater vehicles. And then I graduated in 2018 and I got a job here in Trondheim at Maritime Robotics. And I started as a software engineer and project manager, and now have transitioned in a more R&D management role there. So I thought what might be interesting to kind of make sure we're all like talking in the same frame of reference, is to explain what artificial intelligence meant at the University of Groningen. Because these days, when people talk about AI, especially in the media, a lot of times what they actually mean is machine learning. And that, to me, is not just artificial intelligence. To me, artificial intelligence is way broader. So at the University of Groningen, one of the books we studied as like the AI Bible was Russell and Norvik's artificial intelligence book, which discusses many different things, amongst which intelligent agents, robotics, multi-agent systems, but then of course also knowledge-based systems, problem solving, learning, which of course includes machine learning and neural nets, but also just the more traditional, what probably 10, 20 years ago was seen as artificial intelligence, which is more path planning and knowledge-based systems. So in order to study that, we actually had classes from a wide range of different disciplines. So we had some computer science classes, but actually not that many. And then we had psychology, philosophy, linguistics, physics, mathematics, and then specific classes that were taught by the Department of AI. And the main goals here that they proposed to us as we were like looking at, oh, what do you want to study? Like, what is AI about? They said AI is both about better understanding and modeling intelligence in humans, where then you have a lot of topics that we studied as well related to how do you do cognitive modeling? How do we make models of our brains? How do we store and process information? Stuff like that, as well as trying to recreate intelligence and any kind of artificial intelligence in machines, really. And that is then related to more traditional knowledge-based systems, smart algorithms, robotics, path planning, machine learning, and all those things. And then finally, what we also studied is how do you present that in a good way to the users of the systems. So there were also aspects of usability engineering, user models, UX design, stuff like that. So this is just to give you a bit of a frame of reference. So when anybody asks me, like, what do you do at Maritime Robotics related to AI, like basically all these aspects come to mind. So Maritime Robotics, it's based here in Trondheim. For those of you who don't know, we're in this, I don't know if you can see my cursor, in this building next to Pierbade, basically. And we have been around since 2005 when it was founded by our CEO. And some of the main markets that we develop unmanned systems for is for geospatial mapping, environmental monitoring, transportation, as well as defense and security. So Maritime Robotics makes unmanned systems, trying to make them cost effective and risk reducing. And the first product that we sold was a moored balloon system, which you see in the top right. And that's basically like a big weather balloon with a gimbal camera underneath that can be used to monitor exercises that are done at sea, for example. So it was initially developed for the oil spill exercises that are done every year here in Norway, where they wanted to have a top-down view of what's going on. So then at the same time, as we brought that to the market, we were developing unmanned aerial systems and unmanned surface vehicles. In the middle, you see the unmanned aerial system, the Falk, which is an ongoing R&D project for us in developing that into a product. And then we have several kinds of unmanned surface vehicles. So I just wanted to show you a little bit of these systems and then talk a bit about the R&D work that we do. So this is the Falk unmanned aerial system. It is for one of the main reasons we're developing it, or one of the main design considerations really, is that we wanted to be very flexible to payload integration. So whatever kind of payload you want to put on it, for example, you want to put a magnetometer on it to measure signatures of potential minerals in soil, then it should be possible to do that. Or you want to put a LiDAR on it, either to do mapping of terrain just over land or even in the ocean, then that should be possible. So we're trying to develop a system that's very flexible in terms of what payload you integrate. And then another thing that we're really considering is some of the specific challenges that we have here in Norway in terms of operating in Norwegian and Arctic conditions. So you have to think about the weather here, potential icing, dealing with potentially demanding topography. If you consider all the terrain in Norway, it's not like in the Netherlands where I'm from, where it's mostly just flat and it's pretty easy to fly a UAV. Like here, if you're doing the path planning, you have to actually consider potential mountains that you have to go over. And also when you're thinking about the communication for that, how do you maintain good communication with an aerial vehicle if you don't necessarily have line of sight communications? So there's a lot of work into these different topics, obviously also within our R&D work. I just thought I'd show you very quickly from a research project that we're running where NTNU is involved as well. This is the Marlander project, and the idea here is that you want to be able to deploy and recover the unmanned aerial system from a ship at sea. So deployment or like takeoff, it can be pretty easy. Typically with the aerial vehicles that we run, a lot of times we use a catapult to shoot them into the air. So you could put that on a ship as well. But then you don't have like a runway for the system to come down. So in the Marlander project, we're looking at net landing. This is just to show you a short video from experiments that were done this year. So that's one of our aerial vehicles that basically flies into a net and then hooks into it for a safe landing. This is the UAV perspective. Right. Another thing that we did last year, which was very exciting, is that we again collaborated with NTNU and a couple other partners on doing an unmanned flight along the Norwegian coast that was 200 kilometers long, and dealing with all the logistics and permissions that come to that with that. So it's working with Avinor to get the permissions to fly through commercial airspace, but also making sure that along that whole flight, we had communication to the aerial vehicle, which is not straightforward. There's like an article about this on our website if you're interested in reading a bit more about that. Then in terms of our unmanned surface vehicles, so we have basically 2 unmanned surface vehicles developed at Maritime Robotics. The Otter USV developed for sheltered waters such as lakes, rivers, water reservoirs, or ports. And then the Mariner USV that is more capable for coastal or open waters. And then the third thing we do is conversion systems, which means that we basically make it possible to change any boat into an unmanned boat. We just have to basically communicate with the owner of the boat to figure out the different systems on there and how can we interface with it to basically put the same control systems on it that we have running on board the Otter and the Mariner. So the Otter is a 2-meter long unmanned surface vehicle. One of the main characteristics or selling points really is its long endurance. So it can run up to 20 hours if it's running at 2 knots with the multi-beam. Also, it's really easy to take apart and put back together, so it's easy to transport. So what this might be used for, one of the most common cases that it's been sold for so far at Maritime Robotics is for doing surveys of the seafloor or bathymetry. So here's an example where we did a survey at the dam to basically check in front of the dam how the seafloor, like lake floor, was changing basically, and whether they needed to do any work on it. Another example of a more research project that we did with the Otter and also with the multicopter that you might see kind of in the middle on top of the image was running it with the Ecotone's underwater hyperspectral imager. So Ecotone is also a company here in Trondheim that have developed an underwater hyperspectral imager, and we deployed it on the Otter actually to collect imagery within the water column and seafloor that they then used within a project to do machine learning on it to classify different kinds of algae in the water column. So this is really interesting because in most cases, like a standard sensor to measure whether or not there's algae in the water column, it's just going to tell you whether there's a lot of algae or not, like basically the quantity, but it's not going to tell you about different kinds. And in most cases, biologists have to collect physical water samples and then under a microscope inspect to figure out what kinds of algae are in the water. So yeah, that was a pretty cool project to work on. Then the Mariner is a 6-meter long unmanned surface vehicle that we redesigned recently. It's, as I said, more capable for offshore operations. The first version of the Mariner, it was deployed for several years in the Gulf of Mexico. So here you see a photo of that on the right side. It was deployed off of a big mothership there, and what it was doing was that it was surveying nodes that are on the seafloor, taking seismic measurements, and it basically had to just ensure that all the nodes are operating correctly. So basically, this was a task that before they were actually doing manually, putting people out in a workboat, driving over the whole field with an acoustic modem, pinging to all the nodes on the seafloor, and just checking that they're all functioning properly. So this was one of the use cases that the Mariner was developed for initially, and it's been running there successfully. So over the last 2 years now, I think we basically, based on the experience from there, we redesigned the Mariner and have the new version out now. And then conversion system. Not going to go into too much detail there. Like I said, we can take different boats and convert them so that they become capable of running as an unmanned system. Typically for all these systems, there are several modes of operation. So you can use a remote control like interface, for example, through an app on the phone or through a computer. So most of these systems, we deliver them with either a laptop or a computer that has our vehicle control station software, and that enables many more modes of operation. For example, doing course and speed autopilot, waypoint tracking, station keeping, and also formation control. So this is an example of what that looks like. Here's an example where you see there was a mission planned for the USV, and we also have the live data coming into the vehicle control station, so you can see the map that was made here of the bathymetry, basically. All right, so the more interesting part, I think, for y'all is some of our ongoing research and developments. So there's a lot of R&D topics that are all, I would say this is all artificial intelligence, basically. So we have to kind of, and this we have both for our USVs and aerial vehicles that we have to think about. So basically on the left side, you have the sensors where you have data coming in. So we have to look at doing state estimation for the unmanned vehicle and doing sensor processing. And then the next steps is what do we do with that? So we're looking at how can we use machine learning, but also more traditional sensor processing techniques to extract information out of the data. Then look at, for example, objects in the imagery that you see, how do you do classification on that, potential tracking. Can use SLAM to localize yourself, especially if you're in GPS denied environments, and then trying to use all of that information to increase your situational awareness, which then enables you to do a lot more in terms of autonomous planning, control, collision avoidance, and those things. So these are some scenarios that we use that for. So on the left side, you see the zoom button. So we're in a project for autonomous ferries, basically looking at how can the zoom button be made autonomous. And then on the right side, you see an image from the AutoSea project. So we were involved in the AutoSea project and now in the follow-up, which is AutoSit, which are related to autonomous operations at sea and enhanced situational awareness for unmanned or autonomous ships. So one of the main aspects, as I just showed, is sensor processing. fusion situational awareness, basically improving situational awareness. So this is an example of what we can provide already. So on the top here, I actually have a visualization of the boat and like 3D visualization of the environment to try and give an operator more information on what they're doing. And then in the bottom is actually the graphical user interface that's more typically used with like a nautical chart, an overlay of the radar data, overlay of the bathymetry data. Then you get streams of the camera feeds from that are like on the boat and all that information presented to the operator. So some of the things we're looking at is how can we integrate more sensors into our systems and then use that for more autonomous operations. So I'm just quickly showing you some work from some of the students that have worked with us. So we often have bachelor and master students run projects with us, either semester projects or like their thesis projects. So this is from Øystein Walden's thesis that he published in January. And he looked at how can you use stereo and monocular vision for potential auto-docking operations with the Otter. So this is the vision-based navigation system that he set up to basically have stereo cameras and then run the data that comes from that through deep learning algorithms, in which case he was using darknet YOLO v3. And then from the information you get from that, you can use more classical machine learning techniques such as coordinate detection and post estimation to then aid you in your docking operations. So this is especially important if you don't have very accurate GPS positioning, or even if you have that, you might not have very accurate estimation of your heading and you need to go into a tight space. So then it's important if you can recognize, for example, on the right side, you see here an idea of having markers in at the docking station and making sure you dock properly then. So here are some of the challenges that I thought were interesting in mentioning that he came across. One of the things he noticed is that if you're trying to do this by camera alone, they're actually very sensitive to environmental changes. And then using a machine learning approach, you need to have a lot of training data for a lot of different environmental conditions, considering also in the change of seasons here in Trondheim, how it gets dark more quickly, that it can be raining, snowing, fog, like any of those conditions. And then he also noticed that with the different sensors, it becomes really important to time synchronize in order to be able to do accurate estimation based on the data that you see within the imagery. For the cameras, he was initially using pretty high frames per second, like how many frames are you capturing, because we're used to video being 15 or 30 frames per second. But if you're using that, especially with a bunch of cameras, you end up getting really high bandwidth requirements on your networking interface. So that was also something to think about. And then some aspects that he noted that are obviously of concern is potential cybersecurity, like how do we protect ourselves from adversarial attacks? So you see some examples here, and I put the links in the slide as well if you want to read up some more on this. And that it's actually pretty easy to make an image of a panda be recognized as something completely different by just adding strategic noise to it. So like, how can you make sure that nobody's messing with your camera streams if you have unmanned systems running by themselves where anybody can just try and like hack into the systems? And if you're working with, for example, signs on shore, how to make sure nobody's gonna tamper with your environment and mess up your docking station? So these are some of the aspects that I think he's also looking at more in his PhD now, like looking at cybersecurity aspects for unmanned systems. And then also quickly showing you right now, actually today, Diederik was trying to test this rig that you see on the right side. So he's developing a new sensor rig for our Otter to give us more flexibility in testing situational awareness and sensor processing and sensor fusion algorithms. So what you see there is that there's 2 EO cameras on the side and a LiDAR on top, and then there's going to be 2 more IR cameras added. And one of the aspects that he's addressing is the time synchronization by adding the Sentiboard, which is actually developed a spin-off from NTNU now, initially developed at NTNU as well. And then within this master thesis is going to look more at doing sensor fusion of these different sensors, which, as I said before, in the end, then that can be used again for path planning and collision avoidance. So jumping back to aerial vehicles, very related as well. We're also in a project where we're looking at maritime surveillance with unmanned aerial vehicles. So on the right side, you see kind of a concept of that. So there's potential different applications for this. For example, in marine search and rescue, if something or somebody is lost at sea and you need to quickly find them. But there's also other applications. For example, you might be operating a big ship at sea that is not easily maneuverable and you want to avoid that it runs over anything. Then you could potentially want to send an aerial vehicle ahead to check if there's anything on the sea surface. And if so, then you can route well in advance so that you're not going to run over potential animals or other objects in the water. So one of the difficult things here is how do we ensure 100% detection? So if you want to make sure you're absolutely not going to run over anything. So with a lot of classification problems, you have what you see on the bottom left here. You can have true positives, which is like you're actually detecting what you mean to be detecting. But with any classification problem, you're also gonna have false positives, false negatives, and true negatives. Like true negatives is fine, of course, but the false positives and the false negatives are tricky. So false positive case, you're detecting something that's there, but it's not actually there, or it might be predicted as something else than what you were thinking. Or it's not passing some threshold that you set. So then you have a problem. But the even bigger problem, if we want to ensure 100% detection, is the false negatives. So if we are not detecting something, but it is actually there, then we have a really big problem because let's say a Titanic case, if we're not detecting the iceberg that is there and we run our ship over it, then it's a huge problem. And usually this is a trade-off space when you're training your algorithms, that you try and balance it. So you try and get both of them low. And usually if you want to increase the number or decrease the number of false negatives, you increase the number of false positives, but you ideally do not really want either. So these are some of the problems that we're looking at now. Also developing a sensor pod for the unmanned aerial vehicle, doing the same kind of problems with processing all the data, sensor fusion, stuff like that. Also, if this is interesting to you, we right now are recruiting a student to work on this as well, and there's a post on NTNU Bridge about this. All right, sorry, I think I'm running out of time. So very quickly, some of the path planning and control stuff then that this is being used for. So we're doing work on autonomous collision avoidance. And this is just to show you from the Odyssey trials, that was algorithms developed by PhDs and postdocs at NTNU. And then we're testing it with the Telemetron USV, which was our R&D vessel. We now have a new R&D vessel, basically running in unmanned mode. And you see it here in a standard collision avoidance scenario. So in the top, you see the USV. And in the bottom is the gunnerus, and it has to avoid that in a head-on scenario where basically they're running straight at each other. In the bottom, you see the views from the USV. You see inside the cockpit, which is basically to show you that the people inside the telemetron are not doing anything. Right now, they're standing up and talking because there was actually at this time some pleasure crafts, which you see coming in on the left side, which shouldn't have been there during our experiments, but they decided to just go and play in our experimental area. So the people on board the telemetron were a bit nervous about what was going to happen. But you saw on the right side that from the radar data that's processed on board, it's actually detecting those vessels and considering them in the path planning. So here you see an overlay of the path planning. You see all the different paths it's considering where it could be going, and it's then considering both the objects that are within the space, as well as the collision avoidance regulations that it has to adhere to in order to try and make a safe maneuver. So there's a green line that was just highlighted there, which is like a decision that the USV is making at that time for what avoidance maneuver it needs to do to accurately avoid the gunneress, but also the pleasure crafts behind it. So now you see it diverting from its path. And you can see on the right side that it keeps changing the predictions for what are the possible paths it could be taking, considering objects in the space, and considering that in the end it wants to go back to the route that it was told to take, which was just a straight line down basically. Okay, that was just quick. The videos are on our YouTube channel if you want to see more of that. And yeah, that was basically a quick run through of some of the work we do at Maritime Robotics. So if there's any questions, then I'm happy to answer those.
Yes, thank you, Stephanie. We have got a lot of questions actually. The first one is, why is it important to know the specific color of the algae?
So the color is not necessarily important, but there's certain kinds of algae that can excrete toxins that can be dangerous for the marine life. So you can look this up, harmful algae blooms, HAB, like HABs. There's a lot of articles on this, and there's more and more concern about that because they're becoming more and more of a problem. So there was actually a huge bloom spring of last year in the north of Norway, where there was a massive algae bloom, and then it had a huge impact on our aquaculture there. So obviously, as we're growing the aquaculture industry, not just here in Norway, but worldwide, it potentially has a lot of problems with it. For example, overfeeding in aquaculture can lead to bigger algae blooms, and then that can impact then the health of the fish, but also us, for example.
All right. Another question is, how do you combine classical computer or robotic vision with state-of-the-art deep learning?
Yeah, that's interesting. So one example I think was given in the work that Øystein did. So it's basically you can layer it at different stages. So you can potentially do pre-processing with classical computer vision techniques and then do your machine learning, or the other way around. Also interesting, and I think that's more in research projects where we're exploring that, is doing some of these things side by side and then seeing if you can merge the information that's coming out of it. So there's a lot of different ways in which you can combine them, I think, and it's trying to figure out the way that we can benefit from both. Because if you're talking about doing detection and classification of objects in an image, right now, deep learning is like just nothing can really compete with that in terms of the performance. But there's obvious caveats with the use of deep learning, machine learning, aside from also like needing a lot of training data. So we're trying to figure out, I think worldwide, everybody's trying to figure out how can you kind of make the best of both worlds, and in which ways can we combine the information.
Yes, another question is, have you considered end-to-end deep learning systems deployed for your USVs?
Yes, we have considered it. At the moment, we don't think that's quite the way. There's a lot of yeah, you can have a lot of thoughts on this, and we can have a lot of discussions on it. And our main autonomy lead, Giorgio, I'm sure you can have a very long discussion with him about this as well. One of the potential difficulties with unmanned boats could be the verification, validation, and the certification that we'll need to do in order to let the boats run. So at the moment, there's not a lot of legislation yet, which kind of makes it easier to get away with things and try things. But there's a huge discussion about explainability of AI, explainability of machine learning, and trustworthiness of systems. Today, I was in a full day workshop for the AutoSit project, and this was discussed again as well with the VGL who were present there as well. And they're doing a lot of research and trying to figure out how are we gonna like verify and validate AI systems. And yeah, so that's one aspect. The other aspect is that, yeah, deep learning is great for certain things, but not necessarily everything. Like we actually have really good control systems, control algorithms, and we don't have proof yet that deep learning is necessarily better at doing the control of a marine system. So if we're talking about computer vision, there are certain cases you can show, okay, deep learning is definitely outperforming all the traditional methods. But if that's not the case, then it also becomes a question like, do we want to use it in that case? Like, so you need to be able to see that there's a clear benefit in doing that. And then we're also considering the aspects of, yeah, how are we going to get the systems like out in the world with insurance and everything.
Thank you so much, Stephanie. Next speaker up is Oddvar Husby from Maritech. So are you here, Oddvar?
Yeah, thank you. So I will talk about something very different. I'll talk about machine learning for forecasting salmon prices. And to me, that sounds, having seen you talk about autonomous driving, this sounds very simple. It's just a two-dimensional problem, not three-dimensional. So it should be a lot simpler to solve. A bit of my background: I have a PhD in mathematics from NTNU. I worked with pattern recognition in images. That's some years ago, and after that I've been working in the oil industry, and then last 2 years with Maritech in the seafood industry. And I had the data science department in Maritech. And we're talking about forecasting salmon prices, which is an important price for Norway and for the players in the seafood sector. Understanding the development of the price is very important for planning how you slaughter your fish, when you want to sell the fish to the market, which markets you want to sell to, and so forth. So for both the traders, for the distributors, for the retailers, and for the producers, knowing the salmon price is very important for planning how you act in the market. But even if it is important, it's surprisingly little work done on forecasting. There are some studies, but not a lot of really thorough work on that. So so far it's mainly based on gut feeling and experience when they plan or try to forecast the prices themselves. A few words about Maritech as well. We are a software company that is working towards the seafood industry. We are one of the leading software companies in the world working with seafood. We are mainly creating software for trading and distribution of fish. And in Norway, around 70% of the fish traded out of Norway is traded to our systems. And we have around 100 employees, been growing very fast last years. And we also have a data science department that is working on using machine learning and other analysis techniques for helping our customers in automating a lot of the choices they do in the market. We are located in Molde, that's our head office, and then we have offices a lot of different places. in Trondheim, and mainly then in North America, Chile, Iceland, and different places in Norway. Before I start on the price forecasting, I'll just give a brief glimpse of some of the problems that our customers face in the seafood sector. And that's related to both forecasting of supply and to optimizing distribution of fish and price forecasting. And the number one and maybe most important challenge in the seafood or aquaculture industry is biomass forecasting. So biomass, that's the weight of the fish that is in the sea. And of course, that's kind of the value of your company. If you are a fish farmer, that's in the fish in the sea. And it is surprisingly difficult to know how much fish you have in the sea. It's not like you have a chicken farm or a cow farm where you can count and weigh the animals. Here you have to rely on cameras, and we already see that that's hard to use cameras to count and measure sizes of fish, and you have thousands of fish in a pen, and it's hard to get an accurate estimate of the combined weight and also the size distribution of the fish there. You can also use feed consumption as a measure of growth. But still, with all these techniques, it's up to 25% error in forecasting of the biomass. And that has big consequences because you typically sell the fish before you slaughter it. So you have already sold the fish, then you take it up and slaughter it, and it's maybe less fish than you thought, or it's a different size, different quality than you have thought, and then you already have sold. So you have to start dealing with your customers, selling them something else than that they have bought. So kind of reducing that variance, having better estimates and forecasts of the fish in the sea, that's very important for the industry. And there's a lot of work being done there, both on cameras. We do it in a bit different way. We just use mathematical methods to see if there are systematic skewness in the forecast that they give with the actual fish that they take out, and see if that can be related to weather, for instance, other parameters in the growth rate, and see if we can correct for those skewnesses in future forecasts. So that's one example. Another very important challenge in the industry is distribution. So typically, fish is it's farmed in many different locations in Norway, and it's sold to hundreds and hundreds of customers throughout the world. And a typical customer buys very small amounts of fish, and they are very specific on what kind of fish they want. They want a specific weight class, and they want a specific quality. So the challenge is to match what you have with all the bidders, and then optimize how you distribute the fish to get the most value out of the fish, and also to minimize the logistical effort with bringing the fish to the market. And also you have to keep in mind that the fish is usually flown out fresh, so this has to be done very quickly for the fish to arrive at the customers while it still is fresh. So to illustrate the example, this is if you have a supplier in Norway, it has a forecast. It's going to sell fish at these weight classes, and this is the price that they want for the fish based on weight class. So it's a higher price they want for 6 to 7 kilo than for 4 to 5 kilo, which is the most common weight class. And then you have buyers throughout the world, like here in Rome, you have a buyer that wants 5 to 6 kilos and 6 to 7. And this is the price that buyer is willing to pay for the fish. And then you have similar buyers in, let's say, Tel Aviv or Seoul. And then the challenge is to match what you have here with the buyers in a way that optimizes the value of fish. And that's a project we have ongoing with Møreforskning and University College in Molde to find algorithms for optimizing this problem and automating this process, because now it's done manually typically, and the traders use their experience and they use Excel spreadsheets to try to get this done in an optimized way. And we think it's a lot of to gain by automating this through machine learning or other types of algorithms. Then the final kind of problem is price forecasting. And this is a project that we are ongoing now with SINTEF and with Seaborn, which is one of the biggest seafood traders in Norway, located in Bergen. And I guess, as you know, that forecasting prices, that is very hard. Forecasting anything is hard, and that's why maybe it hasn't been done a lot of attempts on forecasting salmon price. These are a couple of examples that show some of the challenges and pitfalls with forecasting. This is interest rate from Norges Bank or Norwegian Bank. So the red line is the actual interest rate, and the blue lines are the forecasted rates at the given points. And as you can see, the model here is trending toward a fixed point, and the forecasts are not very precise looking back in history. So even Norges Bank, which is a fairly advanced model builder and has probably one of the best teams on this kind of forecasting, are missing the target quite a lot. This is another example. This is from The Economist, which is also a very respected newspaper. They have forecasted the outcome of the presidential election in the United States. And the day before the election, they forecasted 97% winning chance of Joe Biden. And we know now that is turned out to be correct. But I'm not sure if the 97% probability in hindsight is something that they are proud of. I think the real uncertainty there was a lot higher than their models showed. So that's some examples of the difficulties with forecasting. I think I skipped this one. Yeah, well, just very briefly, why does it make sense to forecast the price? Obviously, if you have a fish farm and if you don't know anything about the farm or the price, you will typically select to slaughter an even amount of fish every week and then sell the fish. Then you get a kind of even workload for your people. But obviously, if you know that the price is going up in the 3 weeks, you will plan your slaughter differently and try to postpone as much as possible and slaughter it toward the end of the period so that you make more money on your fish. That's kind of simple and obvious. And if you hit on this 60% of the time or 70% of the time at least, you can predict the direction of the price correctly. A medium-sized fish farmer can easily make many millions a year extra by planning slaughter according to the forecasted price. So that's kind of some of the business case behind forecasting. And you have a lot of other long-term business cases as well. So what are the parameters affecting the salmon price? So on the supply side, it's fairly easy. You have the biomass, which is the amount of fish in the sea. You have the processing capacity, so how much fish can you slaughter at a given day and bring into the market. You have regulations that tells you how much fish you can actually have in the sea in specific locations. You have diseases and parasites, as you know, that will affect the mortality of the fish. So how much of the fish that you put out in the pen will actually live to be slaughtered. And then you have the weather that affects the growing rate of the fish. So warm water, then the fish will grow faster than in cold water. So that's the supply side. And then on the demand side, you have more like seasonal trends. So the demand for salmon is higher around Christmas and Easter, and summer as well. You have the purchasing power in the market. You have consumer taste and trends, exchange rates between euro and Norwegian kroner, and you have prices of alternative food sources like meat and chicken and vegetables. And of course, you also have things like global pandemics that certainly affects the price a lot, and it's obviously very hard to model. And generally, it's kind of the supply side. It's possible to model. You have physical models for the growth. You have physical models for the weather. You can observe a lot of the things there. So it's that part of the equation is easy to, or not easy, but it's possible to model and forecast. Whereas the demand side is a lot harder to model, especially like consumer behavior, consumer trends, and shocks in the market like COVID-19. It's almost impossible to make meaningful models of. So therefore, it's easier to focus on the supply side when doing modeling. As for the data sources for prices, there are just a few public data sources for salmon prices. There's something called the Nasdaq Salmon Index, which is a weekly price collected from Norwegian traders. And then you have the fish pool forward prices, which are future prices in the market. And you have export volumes from SSB or from other, from US and UK and Chile, that gives you some indication of the supply available to the market. So that's the kind of the only data that you have publicly to forecast the price. But then we in Maritech, we have an advantage because we handle all the sales and purchase transactions for most of the players in the Norwegian market. So we have a lot of detailed information on daily sales and purchase transactions. And we think that by using that data, we are able to predict price trends faster than if you just use the public data, which is on a weekly basis. So that's why we are doing in this project, is to use the daily sales and the daily purchase transactions together with the Nasdaq data to see if we can achieve better predictions on the short and medium term for the price. But there are still a lot of challenges with this. One thing is that obviously the data is in different kind of time spans, so you have to transfer it to weekly or daily data from one or the other. You have to deal with the seasonality trends, which is surprisingly hard for the weekly data, since, for instance, Christmas it's not on the same week every year. So if you have weekly data, kind of capturing that seasonality is a bit challenging. Also, Easter is different weeks every year, so you have to do some tricks to affect for that. And then for the sales and purchases, there are also some challenges that I will get back to. And this is the forward price. That's on monthly basis, so that's even another time scale that we have to factor in if we are to use that kind of data. And these are the daily prices from one of our customers. So these are daily sales prices to the right and purchase prices to the left for different weight classes of fish. And there's a lot more detail in these data than in the Nasdaq data. And that's where the interesting information is, we believe. But you can also see it's a lot of noise in the data. And that's also the challenge here, to make sense out of this data. Another challenge is that typically purchases are done to be sold next week. So you have to factor in that the kind of the price assumption for a purchase is different than for a sale. So you have to find out what's the time. If you do a purchase today, what sales price are you looking at then? Is that the sales price next week or in 5 days that you are actually trying to capture in today's purchase price? So you have to kind of find the right lag between purchases and sales to make meaning out of that data as well. And that's typically what we see here in a project like this, that, and I guess that's for all machine learning projects, is that a lot of the work is just in cleaning the data, making the data in a state that it's can give us meaningful prediction. So it's easy to kind of talk about the methods and the AI, but just getting the data in, cleaning out the data, taking out sales and purchases that are not relevant for the spot price. That's a lot of job to do that in the right way, to make sure that you capture the right prices. Yeah, I see I'm starting to run out of time. Method. So obviously, for forecasting time series, one simple method is just a name method. The price tomorrow is the same as the price today, and that's a surprisingly good method. It's hard to beat that method. And then you have regression models, obviously, and more machine learning type neural networks. Yeah, and of course you have the futures as well from Fishbowl. And we have looked at different methods. This is just a quick review of things that we have tried. We tried the profit from Facebook and various other methods. And the blue line here is the actual price, and the green line here is long short-term memory model, which is the type of model we think is the best for forecasting prices. It's also been used for stock prices, for instance. So it's a type of method that seems to work well for time series. And I'm sure that most of you know this better than me. So I won't spend a lot of time on that. Long short-term memory method, it's a kind of a neural network method that tries to capture history in a better way than ordinary neural network. So to keep important learning from kind of far behind in the time series, to make sure that you capture or keep important data going forward in the future. And kind of obviously the pro with that is that it is a flexible method. It can capture long-term effects. And the drawbacks is that you have a lot of parameters to tune. It's a difficult model to fit maybe, and it also is time consuming to run. And also, as you also might know, that LCM models is used a lot, especially in speech recognition. So typically for long sentences, like this one, she grew up in Norway. Now she has been in China for a few months only. She speaks fluent ... That's a kind of a problem where you need to have more of a long-term memory to be able to predict what should be the next word in that sentence. And LCMs are being used a lot in kind of things that we are familiar with, like in Google Translate, Alexa, Siri, and Facebook uses a lot of LCM transactions every day in their algorithms. So we have been starting to work on that for price forecasting. This is just kind of one-day prediction with a model, a univariate model where we only predict based on the data itself. Obviously, a one-day prediction, it's not too hard. So this is an okay fit of the model. But ideally, we would like to use multivariate models where you input both the purchase data and the sales data and Nasdaq data and maybe other sources as well to predict the price. Because we think both the purchase data and the sales data has separate information that can affect the price. But we see that kind of multivariate models is a lot harder to make work well. So we're not finished with finding a good way in doing that. So that's kind of the work that is being done now together with SINTEF. Yeah, we see that kind of data cleaning and model fitting is much more complicated with the multivariate models. This is some kind of brief examples of what we've done so far. This is based on a student project done this summer, so we haven't any data from the SINTEF study so far, but this is a 14-day prediction of the price based on this history, and the light blue is the kind of the actual price for that period. So it doesn't seem too bad in this case. And also here you have on the right a 14-week prediction. There you see the model is maybe kind of overfitting a bit, but still here as well, it looks promising in this example at least. So I think it is possible to make meaningful predictions on the short and medium term using an LSTM model. Yeah. And to summarize, from what we see, it's difficult to beat the naive seasonal forecasting for very short-term forecasts like 1 week. But still, it seems like LSTM models are promising for shorter-term forecasts, like let's say 2 weeks to 4 weeks. And it seems that it's possible to achieve hit rates at least 60%, which indicates that it's possible to make money on forecasts like this. Some of the challenges that we need to work more on is to fully utilize the information that we have in the detailed price transaction data. We also have some challenges with unpredictable supply side shocks effects. Typically, if you get lice in a certain location, they have to slaughter everything at once, which is unplanned. And then that could affect the price that week because you get a lot of extra supply in the market. And the question is, can we use weather data and public fish health data to predict those kind of shocks as well? And can we use that data in the model to try to factor in those supply shocks? So that was all I had. Thank you.
Thank you, Oddvar. We have gotten some questions here for you. And the first question is, have you looked into graph neural networks for forecasting?
No, we have not. But that's a good tip. Thanks.
Yes. Another question is, have you noticed a specific trend regarding which parameter has the biggest impact on the biomass forecasting?
Yeah, I think like obviously feed usage, that's the kind of most that's the strongest parameter you have. Depending a bit of the camera solution, if you have a good camera solution, that is valuable data. But apart from that, just the feed consumption is the most important.
Thank you. And a last question here is for students who want to work in Maritech. Do you currently have any positions out?
We don't have anything out, but we are definitely interested in anyone that are have good skills. So it's just possible to contact us, definitely.
Nice, thank you. So now I will share screen. Yes, so that was it for us for this talk. Let's see. This was our last event for this semester, and we want to thank Oddvar, Rudolf, and Stephanie for presenting. And also, we'd like to thank you for watching. I hope you will follow us for the next semester as well. We have plans for some exciting events. So if you follow us on Facebook and Instagram, you will get notified when these events are out. And also, I would like to remind you to answer the quiz to have a chance to win some nice prizes. And again, thanks for watching. We will see you next semester.
Thank you. Bye-bye.
Bye.